Hello everybody, and welcome to video tutorial number 2 on how to do exercise 13, the atmospheric mean. This is the second worksheet that you guys are supposed to be doing um, for the class during the hiatus period. This one should be a little bit easier than the first one because with the first worksheet, you guys, I didn't print the thing directly out of the book. I kind of gave you guys a student version, and it didn't have as much explanation, and I apologize for that. I didn't realize that until after, well, quite frankly, after I made the video. So this one actually should go a little easier. If you notice that we have these areas like this, you need to read those areas. Those areas actually tell you how to do these things, and make sure that you recognize words like um, solar radiation and things like that. Notice that those words in bold, they'll typically show up down here where it says terms. Um, so, with that said, make sure that you're going through and you're reading those. Make sure that you're actually kind of taking note of each of these terms. Um, Read through the introductions. Each section of questions have a reading that goes with it, and within that reading, it'll either explain to you how to do it, or it will go through and give you the information you need to answer the questions. Also, make sure that when you're doing this, is that you recognize when it says figures, like it says right here, figure 13.1. Now this is going to be interesting. There's a little bit of a delay between me talking on the video and the camera. I just put my hand like that. I removed it, and there's about a 2-second delay between what I'm doing. So bear with me while I do that. All right, so let's go over this. So make sure you go over the terms. The first part, the introduction part, is really kind of talking about what we talked about with the first assignment, and also, as usual, with the videos. Make sure you watch the videos before you do this assignment. All right, so here we go. The first 3 questions really have to do with the things that we've already talked about. Intensity of solar radiation. Really what we're talking about, intensity of solar radiation, is the angle in which the sun's hitting down. Remember from the lab, I told you guys that the angle in which the sun is hitting you has a lot to do with how hot the surface of the earth heats up. If it's hitting at a direct angle, you're getting a lot of sunlight over a small area. However, if you're getting that light hitting at a lower angle, that means that light, remember from the last lab, you had a small amount of area. If you're being hit at about a 90-degree area, that same amount of sunlight is spread out over a greater area if you're getting hit at an angle. And if you're getting hit at a really low angle, that's a very large area that will be spread out. So the angle of sunlight is, or solar radiation is another word for sunlight, is very important as to how warm you're going to heat up a surface. Duration, well, duration is really kind of talking about a time, so we're really just talking about how long it's going to take, how long you expose to that sunlight. In other words, how long is your day? You know, is it like the winter where the days are really short, or is it like the summer where the days are really long? That really can affect how much the surface is heated up um, by the Earth. All right, so it says complete figure table 13.1 by calculating the noon sun angle. So that is located at the bottom of the page right here. This is table 13.1, so that's the one that you're looking for. And March 21st, that is the first day of spring, so we know that the sun's directly above the equator. 0 degrees latitude is the equator. So we know the sun's directly above it, so that's going to be 90 degrees. How long? Well, everywhere on the first day of spring and the first day of autumn, everybody on the earth gets 12 hours of daylight and 12 hours of nighttime. So, for 40 degrees north, now I'm going to flip this piece of paper over. For 40 degrees north, if this is the earth, okay, this is the equator. If the sun's hitting the earth at a 90-degree angle on the first day of spring, if you are at 40 degrees north, so here's 10 degrees, 20 degrees, 30 degrees, 40 degrees. That means the sun's going to be hitting you at this angle, but the Earth is not like this. So if you were standing on the Earth and you were looking straight up, this would be 90 degrees. You would have to look down to the south to see the sun. So the sun at 40 degrees north is never going to be directly above you. So what angle are you looking at the sun? Well, if this is 90 degrees and you're 40 degrees north, which is 40 degrees angle from the center of the Earth, that means it would be 90 minus 40. The angle in which you would be looking at the Earth would be 30 degrees, and you would be looking to the south. So you would write down 30, I'm sorry, I said that I did that wrong. 90 minus 40 is 40, let's see, 40 degrees north, 90, 9, 8, 7, 6, 5. Sorry, 50 degrees, not 30 degrees. So 50 degrees. So 90 minus 40 is 50 degrees, and you're looking to the south. So you would write 50 degrees to the south. Now, if you're 40 degrees south, it's really going to be kind of the same thing. If you're looking straight up, you're looking this way, but now you're having to look to the north to see the sun at that same angle. That's how you figure that out. Okay. On June 21st, that's your first day of summer. And remember, that's from last assignment. That is when the sun is 90 degrees to at 23.5 degrees north. Please don't pay attention to the answer that I got written down here. Just scribbles. So at 23.5 degrees north, that's about right here. 23.5 degrees north latitude. That means the sun is heading at a 90 degree angle here. So that's a 90 degree angle. All right, so if you're at 40 degrees north, now the sun's going to be at a higher angle because now the sun is up here. It's going to be more like this. So what angle are you looking at? Well, the difference between 40 degrees and 23.5 degrees, that'd be 40 minus 23.5. That would leave 0.5, 10, 9, 8, 7, 6. That would leave about 16.5. Subtract that from 90, so 90 minus 16.5 would be, should have figured this out before I made this video, huh? 9, 8, 7, 10, 6, 4, 3. 73.5. So you would be looking at a 73.5 degree angle. So on the first day of spring, if you're at 40 degrees north latitude, you're looking at the sun at a 50 degree angle, much lower angle. If you are the first day of summer, now you're looking at a 73.5 degree angle. The angle is much higher in the sky. And that's what you're doing here. All right. So using that table, this table right here, which I think is a little bit off of your screen. There we go. Using this table 13.1, you want to answer these questions. Actually, you want to use figure 13.1, so we're going to move ahead. So make sure, once again, make sure you read this part. Make sure you read this stuff. Know what greenhouse effect is. Know what terrestrial radiation is. Now we go to questions 4 through 7. And you're looking at figure 13.1, not table 13.1. Figure 13.1 is on the next page. Here you go, figure 13.1. You are looking at this picture right here. And what it's showing you is all the incoming solar radiation. So if we have 100% of the sunlight coming and hitting the Earth, 50% of it's going to be absorbed by the surface of the Earth. 22% of it's going to be reflected by clouds. 3% of it is going to be reflected by the Earth's surface. 5% of it is going to be scattered by dust particles and stuff like that in the atmosphere. Which means if you take all these stuff that's reflected back into space, 30%, which is actually question number 4. What percentage of solar radiation is reflected and scattered back into space? Well, there's question number 4, the answer right there. All right. Question number 7, what percentage of incoming radiation is absorbed by gases? Well, absorbed by gases. It actually says that in here. Let me read that question again. What percentage of solar radiation is absorbed by gases in the atmosphere and clouds? Well, that's going to be given to you right there in the picture. It tells you straight up what it is. What percentage of incoming solar radiation is absorbed by the Earth's surface? Well, there's the answer to that one right there. So that's 4, 5, and 6 right there. And then you're going to have to figure out, read question number 7. You're going to have to figure that one out for yourself. All right, question number 8 and 9. It says use your text. Basically, I'm going to just go ahead and talk to you about what this is. In the videos I went through, when it says use your text, it's going to be like refer back to the videos that I made earlier. So we have these things in the atmosphere. You basically have different forms of radiation that comes from the sun. You have ultraviolet radiation, that's the stuff that causes sunburn. Most of that is absorbed in the upper atmosphere by the ozone layer. And we'll talk about the ozone layer a little later on in this assignment. You have visible light. That is a form of radiation. So what you see, the light. And of course, if you're seeing it, that means it must have made it to the lower part of the atmosphere. And then you have infrared radiation, which is heat. And heat is what you get when the Earth absorbs visible and ultraviolet light and turns it into infrared radiation, which is heat. All right. So the first question number 8 says a shortwave radiation that passes through the Earth's atmosphere and is absorbed at the Earth's surface is what form? Well, I just told you that ultraviolet light was absorbed in the upper atmosphere, so most of that does not make it to the surface. Infrared is the heat. Well, that's what you get once you have absorbed it. So which one's being absorbed? Well, it must be visible. All right. So the next question is number 9. When the surface releases solar radiation, it has absorbed. The long wave radiation is probably, so ultraviolet is very, very short wave radiation. Long wave radiation would be infrared. Visible would be somewhere in between. So what's the long wave radiation? Well, the one I just told you. Look at this. I'm just like straight up giving you guys some of these answers. Okay, question number 10. Ultraviolet visible radiation are absorbed most efficiently by the lower atmosphere. So I just told you guys that the one wavelength that's absorbed by the atmosphere is the ultraviolet. And then we have this question about greenhouse gases. Greenhouse gases are gases in the atmosphere. Not all gases in the atmosphere absorb sunlight. That's why it makes it to the surface. However, there are gases in the atmosphere that do absorb sunlight. Carbon dioxide absorbs sunlight, and it takes that sunlight and converts it into infrared radiation or heat. Water vapor, sulfur dioxide, carbon dioxide. What am I missing here? Water vapor. Oh, and methane. Those are the big greenhouse gases that we worry about, because the more of those gases we have in the atmosphere, the more sunlight's going to be turned into heat. And we can only live in a little range of heat. If it gets too hot on the Earth, we as humans can't handle it. If it gets too cold on the Earth, we don't have enough of these greenhouse gases, then we can't handle it, and then we have mass extinctions. Most of the animals die off. So we can't have too many greenhouse gases, but we can't have not enough greenhouse gases. Greenhouse gases is what keeps our temperatures somewhat stabilized. The problem is that due to industrialization in the last couple of 100 years in the world, we have been putting more and more carbon dioxide gas. And unfortunately, this has a kind of negative feedback loop, or I should say positive feedback loop, in that the more greenhouse gas that you add, the more carbon dioxide you have, the more it heats up the atmosphere. The more you heat up the atmosphere, the more you start to melt things like glaciers and ice off of land in places like Canada and Siberia and Antarctica. And underneath that land is old, rotting, decaying forest that's been trapped by ice, but now that ice is gone, and now it's releasing methane, which is an even worse greenhouse gas. So that causes more global warming, more greenhouse gases, more global warming. And of course, the more that you heat up the atmosphere, the hotter the oceans are going to get. The more the oceans get hot, Well, that's going to put water vapor into the air, which is, guess what, a greenhouse gas. So right now, the reason why you hear so much about the greenhouse effect in the news and global warming and so forth is because we're kind of careening out of control. And if we don't figure out how to control the greenhouse gases, we won't have very many more generations of humans here on the Earth. It's going so fast that we can't do it. So now, based on what I just said, you should be able to answer question number 11. What are the greenhouse gases? Now, not all gases are greenhouse gases. Oxygen is not a very good absorber of light to turn it into heat. It just goes right through it. Nitrogen, which is something like 78% of our atmosphere, is made up of nitrogen, and thankfully that's not a greenhouse gas because we'd be, gone. We'd be Venus by now if nitrogen was a greenhouse gas. And since it's most of our atmosphere is that, we don't have to worry about nitrogen. Okay. Just realized, yes, guys, I still drink this stuff at home too, not just in front of you guys. Felt like that was an ad. All right. Question. Moving on. Still referring to figure 13.1. If the noon sun is at 90%, the solar radiation would have to penetrate a greater or lesser amount of atmosphere. This is a really good question. And this is a question I get from a lot of students. Says, Mr. Lee, why do we have red sunsets? Why is the sunset red? Or why is it moon orange when it's on the horizon? It has to do with the thickness of our atmosphere. Now, our atmosphere is about the same thickness all over the world. But the amount of thickness that the atmosphere has to go through changes depending on what angle the sun's hitting. And how does that make sense? Well, if this is the Earth and this is the sun, now I'm going to exaggerate this. I'm going to say that this is the atmosphere that goes around the Earth. Okay. Now that's way too thick. The atmosphere is almost like an eggshell if I were to actually draw that. But if this is the atmosphere that goes to the Earth, here's the sunlight. The sunlight's going to come and hit the Earth. And if you're standing right here on the Earth, you're getting that most direct sunlight. What I want you to know, some of that sunlight is kind of scattered off into the air. Usually the reds, the blues and the greens. And that's why we see blue skies, is because light is being scattered. The blue light from the sun is being scattered all through the atmosphere. But most of the light, except for a lot of scattered stuff, makes it to the surface of the Earth. Now, let's say it's a little later on the day. So let's say that the Earth is spinning this way, and now you're over here. So there you are on the Earth over here. Now the sun's still in the same place, right? There's the sun right there. Sun's in the same place. So now when the light comes from the sun, it is going to travel through, look how much more atmosphere it has to travel to get to you. It's now hitting you at a lower angle versus a 90-degree angle. It's hitting you at a lower angle, and it has to travel through a lot more atmosphere, which means there's a lot more scattering of light. So we lose a lot of blues and greens. So this might be about the time where the sun is just about to set, because anything on this side of the Earth is going to be dark, right? This is night. So the sun is about to set. All the blues and the greens have scattered now, and what you get is the reds and the oranges are the only colors that we have left. And that's why we have sunlight, is because the sun has to go through so much more atmosphere. It's also at a lower angle, has to travel through more atmosphere, and that's why it starts to get cooler right around sunset, the lower angle and the more atmosphere that it has to travel through. So the higher the angle, the less atmosphere that you have to go through, which means we're getting more intense solar radiation. And that conversation will actually go through and answer questions all the way up to number 18. So kind of logic what I just set out and get you off to question number 18. All right, the next part, the nature of the Earth's surface, has to do with something called albedo. Albedo is the ability of the Earth's surface to reflect light. If you have a high albedo, that would be like a white surface, like a glacier surface. most of the light's going to be reflected right back off in outer space, which means it's not going to heat up the Earth. And if it's a dark surface, like a black surface, that's going to absorb light. And if you watch the videos, I took a picture of a white shirt and a black shirt, and then I took a thermal image, and you saw that the black shirt got so much, was about 20 degrees hotter than the white shirt was, because the white shirt has a higher albedo. It's reflecting the light, not turning it into heat. The black shirt absorbs the heat and absorbs the radiation from the sun, the light, and turns it into heat. And that's what we were supposed to do if we were in class. This is what we would be doing in class, is this little experiment where we take a light, a 100-watt light bulb, and we have a black can, like a soup can, and a silver can. So there's a black can and a silver can, and we aimed it at that. And what we got as a result, I wish you guys could do this at home, but I realize not everybody has, well, you probably have soup cans, you probably can get sand, and you can probably get a light. The strange thing is a lot of people don't have a thermometer. So let me just basically tell you what happens here. With the black can, it's absorbing more radiation, so the temperature inside the black can gets hotter than the silver can, which is a high albedo, which is reflecting. So you don't have to do questions 29, 19, 20, 21, 22, 23. You don't need to do this little table at the bottom. I don't need to do that either. I'm going to kind of zoom this back a little bit. There we go. You don't need to do that table on the bottom. And you don't need to do this chart unless, of course, you just happen to have some thermometers, cans, and lights around your house, which, go for it. It's actually kind of fun to do. Then there's the land and water heating experiment. If you've been watching the videos, you can see I talked about the differential heating, how land gets hotter faster, but it can only store about 2 or 3 inches of heat, whereas water warms up slower, but because it's able to mix, it can go further. And then we were supposed to be doing an experiment where we were taking, once again, a light and heating up land and water, and we noticed that the land heated up faster than the water, but when we turned off the light and let it cool, the land cooled off faster than the water did. So that was questions 25 through 33, so you don't need to do those. You don't need to do the table, unless, of course, you've got those things and you want to try to do it yourself. Okay, so that leads to the next part, the daily temperatures. And by the way, this chart right here has to deal with that the water and land experiment. So this says figure 13.7, which is on the next page. Figure 13.7 is this right here. So we're looking at 13.6 and 13.7. And figure 13.7, the cool, oh wait, did I miss something? Oh, I'm sorry, 26 through 30, you do have to do this one. That refers to 13.6. That's no longer the experiment anymore. 13.6 is looking at this table right here. And this is the temperature of 2 cities. And I like to think of the red line as Seattle. And I like to think of the blue line as Spokane. Oops, there's only one E in Spokane. I make the mistake all the time. So Seattle's right next to the ocean. And so our temperatures reflect what the ocean is. So if we look in January, the average temperature in Seattle is about 52 degrees Fahrenheit. It's kind of our average over that entire month. It's the days and nights, cold snaps, warm snaps, and stuff like that. In the summer, our average is just a little bit above 60. As we go into the summers now, you'll notice that, yeah, we get a 70 and 80 degree day every once in a while. Sometimes we even hit 90. But we usually never get, we kind of get maybe close to 70, but on average, it's not that warm. Now, that's in the summer months. So we go back to the winter months, we're back to cool. If you live in Spokane, if you live on the other side of the state, and if you guys planning on going to Washington State University or Eastern, or any of the colleges on the other side of the state, what you'll notice is something really different. Because they're landlocked, there's no water around them, their temperature is not controlled by the water. So in January, their temperatures get, on average, below freezing. So January and December, they're below freezing. However, during the summer, Spokane gets a lot hotter than we do around here. Their temperatures, on average, are pushing 80 degrees as an average. Okay, So that's what questions numbers 26 through 33 are answering. It's just looking at cities A and B, where city A would be like Seattle, B would be Spokane, and looking at that graph and seeing what's going on with that. Now, if we look at the daily temperatures, this might be the daily. This might be today. All right. If we looked at the temperature today, we might see that. This would be about midnight right here. At midnight, it was about 61 degrees. And then as the night progresses, we get to like 1 o'clock, 2 o'clock, the temperature is going down. So why is that? Well, the sun has gone away. We're at night. We're not taking any new solar radiation. So any kind of heat that's on the Earth is being given up by the Earth. And it's just going back off into space, giving up its heat, and it's going back off into outer space. Yes, you can hear my dog barking in the background. We're probably getting a delivery right now. All right. So when is the coldest time of day? A lot of people think that's the middle of the night. It's not. The coldest time of the day is that moment just before the sun comes up. You guys probably experience when you guys come to school in the morning, right before the sun comes up, that is the coldest part of the day because the Earth keeps giving up heat, keeps giving up heat, keeps giving up heat, and it doesn't have any heat to add to it. Once the sun starts coming up, then the sun starts adding that solar radiation. We start to heat up, heat up, heat up. So when is the hottest part of the day? Is it at 12 o'clock noon when the sun's at its highest point? Well, when the sun's at its highest point, that's when we're getting the most intense solar radiation. However, at 1 o'clock, the sun's still high, and it's adding more heat to the heat that we've already had. And it keeps doing that until about 3 or 4 o'clock. And then it starts coming back down as the sun goes down because the angle becomes less than the angle becomes so much less that it becomes less radiation coming in than us giving it back off into outer space. So that's what questions numbers 34 through 40 are asking, is why we have those kinds of days. Okay. All right. All right, that moves off to this next picture. This is figure 13.8. And what you're looking at is what's called an isotherm. This is, if we follow this line right here, that means it would be 25 degrees Celsius everywhere along that line. And what we're looking at, this is the isotherms for January. This is the isotherms for July. So this is winter, our winter. This is our summer, okay? And if we look at where we live, we're kind of right here in the green, which is somewhere between 0 and 5 degrees. Remember, that's in Celsius. That's our winter time. If we look at our summer, we go from green to Seattle looks like we go to yellow. Not a big difference when you take into consideration a place like Minnesota, which is in the blues right here, which is around negative 10 degrees. And they go all the way up to about 20 degrees Celsius on average during the summer. That's a great point. Just like Seattle and Spokane, there's a big difference between it because they're landlocked. In fact, if you look at Siberia, Siberia has some of the coldest temperatures in the winter, but in the summer, they actually get about the same temperatures that we are, close to the same temperatures that we are. So if you ever lived inland, if you ever lived in a place that's inland, you'll see there's a really, really big temperature difference between summer and winter. But if you live in a place like, for example, San Diego, there's not very much difference between summer and winter. In fact, places like San Diego, which is right next to the water, if you live right on the coastline there, it's like they don't even have seasons. There's just so little of climate variation. Now, notice that in the southern hemisphere, it's just the opposite. During our winter, Australia is having their summer. That's because the Earth is now tilted differently than our summer, which is their winter. You can see is considerably cooler. So that, looking at this isotherm map, this is where you're going to answer those next few questions. It might ask you coastal Norway, Siberia. So here is Siberia right here. Coastal Norway is located about right here. So those are the two places that they're asking you to look for. Make sure you use Google Maps if you don't know where those places are. Temperature changes with altitude. Altitude is how high you're going up. And as you could probably guess before, we've talked about this before, the higher you go up in elevation, the cooler the temperature. If you've ever driven up to the mountains, you'll know that it's cooler in the mountains than it is down in like the shoreline. And the reason why that is because, well, the Earth is being heated, the solar radiation is being absorbed by the Earth, turned into heat, and that's what's heating up the atmosphere. And if you jumped in a balloon and you started going up and up and up, it would get colder and colder and colder. As it gets colder, it's kind of a set temperature. The higher you go is going to be this many degrees less. This is called the environmental lapse rate, which is written right there, the environmental lapse rate. How much colder it is for how high that you are. And the environmental lapse rate, they will give it to you what it actually is. I think it's a little bit later on. Yeah, it's a little bit later on. But that only works in the lowest part of the atmosphere. Now, question number 55 says, label the troposphere, mesosphere, stratosphere, and thermosphere in this picture right here. You either need to go back and look at my videos to figure out which layer is which, or you need to go on Google. You can even type in Google Images, and it will actually give you what it is. But this line right here represents the temperature. And what you'll notice that if you're here at the surface, as you go up in elevation, the temperature gets cooler and cooler and cooler and cooler at a set rate. And it tells you what that rate is. It's about 6.5 degrees Celsius per kilometer, or 3.5 degrees for every 1,000 feet that you go up. That's how much the temperature drops. But a weird thing happens after we get to about 10,000 feet. And this is the troposphere right here. So there you go, I'm giving you one of the answers right here. You enter what's called the stratosphere. I'm not going to give you all the answers. You're going to have to figure out the rest of them. You have to do a little research. But notice that when we hit the stratosphere, the temperature kind of stays the same. In fact, it gets warmer. The higher we go up, it gets warmer. So what's going on here? Well, that's this stuff right here. In the stratosphere, there is this gas called ozone, which is basically 3 oxygens instead of 2. We breathe O2. Ozone is O3. And what O3 is an effective absorber of ultraviolet radiation. This is the ozone zone. We don't want ozone down here because it's a greenhouse gas when it's down here. However, up in the stratosphere, it absorbs ultraviolet radiation and turns it to heat. That's why the temperature is going up during that time. It's because it's absorbing ultraviolet radiation and turning it into heat. The closer we are to the sun, the more ultraviolet radiation it's absorbing. So we don't want that absorber of heat down here because that's going to be a greenhouse gas and that's going to be bad. But we do like the ozone layer up here because what it does, ultraviolet radiation is dangerous to us. This is what gives us sunburn. This is what gives us skin cancer. If we don't have ozone up here, and we had a problem a few years back of the ozone layer disappearing, it has come back. It's definitely on the rebound. So that's good news because without ozone, we're subject to this dangerous type of radiation, ultraviolet radiation, and that could kill a lot of life on Earth. So that's what the ozone's doing, and that's why the temperature is going up. Once we go past the ozone, once again, the temperature starts to go down as we go down. This is a little bit misleading because they're measuring the temperature of the molecules, not how cold it really is. But the molecules are so far apart that they probably wouldn't even be touching you. So I talked about that in the video, so you need to go back and look at that. So I talked about ozone. We talked about that. You're going to have to do some stuff on reading at. You're going to have to figure out what the temperature is at what elevation on some of these questions. And then finally, the last thing that we have here is wind chill. Wind chill is, if you've ever noticed, it could be 60 degrees outside and you go outside and, hey, it's nice and comfortable out here. But if it's 60 degrees and the wind is blowing, you'd be like, oh my God, it's cold out here. And that's because your body puts a layer of heat around it. And with that layer of heat, that layer of heat acts like a blanket and it keeps you warm. Well, the wind blows off that layer of heat, you lose that warmth. And when you lose that warmth, then it's going to feel colder than what it actually is. So we call this wind chill. And I have a wind chill chart right here. And it just says, okay, if it is 25 degrees Fahrenheit outside, how cold is it if the wind is blowing at 25 miles an hour? So if it's that's 25 miles an hour, it's a pretty good windstorm, right? So at 25 miles an hour, the feel like temperature, the temperature it feels like is negative, well, what was it? Negative 15. Okay, so that would be your wind chill equivalent. And that is it for this lab. So once again, if you guys have any questions, feel free to email me, askmeonremind.com. This one hopefully goes a little easier than the next one. Don't forget that if you take the tests, once you get done with this and you've watched the videos, take the notebook tests, you need to let me know, you need to email me and let me know that you've taken the second test. I should have there's one more worksheet that I have already posted as of right now. That should be available to you guys on the internet sometime later this week. That said, you guys take care, stay well, love you guys, miss you guys, and I hope to see you guys next year. Talk to you later.